In the previous part, we tried to understand uh, matrix operations and their properties, and also we tried to formalize the algorithmic process to solve the system of linear equations, which was Gauss elimination with Beck substitution. So, we'll in this particular video, we'll try to move one step forward in solving the system of linear equations through computers by understanding more about the matrix multiplication, because matrix multiplication is evident and it's more important, most important, while solving the system of linear equations with matrices. So the matrix multiplication is here what we are going to understand. Now, once we get to understand matrix multiplication, we want to see where it can be utilized in the Gauss elimination process. So, just to give you a hint that matrix multiplication is important in solving the system of linear equations, you just remember that in chapter or in the part 2, basically we arrived to a matrix equation from the system of linear equations. So we said that there is a system of linear equations, and then we come up to and say that it is equivalent to ax is equals to b, where a is a matrix, x is a vector, and b is a vector. So a is a matrix multiplied with another matrix, since vector is also a matrix, so it multiplies with another matrix and generates another matrix, one more matrix, right? So that's how there is somewhere matrix multiplication is involved. So we will try to understand the two views of matrix multiplication. One is the column view, another is row view of matrix multiplication. So this part is dedicated to this understanding. So let's suppose that I have two matrices A and B, and now you want to multiply them. So you can see that this is what we usually do. So A times alpha plus D times beta, B times alpha plus E times beta will give you the second row, and C times alpha plus F times beta gives you the third row of the product matrix C. Okay, now can we visualize this particular product in this way, that the first column of matrix A is multiplied by alpha, the first element of the matrix B, plus the second column of the matrix A multiplied by the second element of matrix B, right? So and you can see that it is quite giving you the same result as the matrix multiplication we did earlier, and we understand in the way earlier we do, right? So just to see an example, there is one column and there is another column, and we tried to make a linear combination. So we said 1 times the column 1 and the 2 times the column 2 of matrix A gives you the column matrix of the product. Okay, so whatever we try to do or we have done here, we'll just try to summarize this. We say that the product of the matrix is a linear combination of the column of matrix A. So A is the first matrix, and the left hand side matrix, B is the right hand side matrix. So we say the product of the matrix is linear combination of columns of the matrix on the left, that is A, and the combination that has to be given by the matrix B, the alphas and betas. So by what amount you should scale is given by B, and what should be scaled is given by A. So that's how, that is the basic idea of matrix multiplication. Can we see similar idea in columns? Okay, let us just try to transpose this whole business. the whatever we have said over here, we transpose. When we transpose the things, let us suppose if I transpose a multiplication a into b, I want to transpose it, then it becomes b transpose a transpose. And you understand the transpose thing, how to transpose and what is the meaning of transpose from the previous lecture. So you can take it from that. Okay, just look at this transpose part. Now transposing the both the things in uh, both the sides, what we get is this. So we said that, or we see this, the call or the row of the product matrix is a linear combination of row matrix or the rows of the matrix on the right hand side, and the right linear combination is given by the elements of the matrix which is on the left hand side. So the left hand side is alpha beta, which is providing you the linear combinations. So you see alpha times ABC. ABC is nothing but the first row of the matrix on the right, and that is b, that is here b. So if here again we say that a b is equals to c, so the a becomes alpha beta and b becomes the 2 cross 3 matrix, and the product becomes alpha times the first row of B matrix and beta times the second row of B matrix. And that's how you get the row matrix, row matrix of the product. Okay, so what is important is the word linear combination. So let us try to say it or define it properly, because we have not yet defined it so properly. So let's try to define it. So when we say it in simply, in simple terms, we say that whenever you take a collection of vectors, you scale them by some quantity, maybe different, and then you add them up. That is called, the generated vector is called the linear combination of that collection of vectors. So that is what it means. So mathematically, if we say that, it means like let V be a set of vectors, V1 up to Vk, then C1 up to Ck are some real numbers or some scalars values, then C1 V1 plus C2 V2 plus and so on Cv and Vn is the linear combinations of vectors V1 V2 V3 Vk. So this is the definition of linear combination of vectors. Okay, so this is the crux of this video, and we will try to understand with some examples. So till now we have done only for one row and one column. So in the product matrix, either we have one column or we have one row. So let's try to have more rows. So let us see that this question. Can I ask you to find out the matrix on the left? Because you see, whenever we are working with the rows or we want to make the linear combination of rows, then we have to make the right linear combination in the left hand side of matrix. And if we want to work on columns, a linear combination of columns of a matrix, then we have to put the multiplier on the right hand side of that matrix, right? So you can see here, we wanted to work here for columns, linear combination of columns. So the combinations are given by B, which is on the right hand side. And in the another case where we are working with the linear combination of rows, you can see that the combinations are coming from the matrix on the left, and the rows that we are going to take, for which the linear combination has to be generated, is on the right hand side. Okay, so we want to generate rows, so the multiplier has to be on the left hand side, and the actual matrix has to be on the right hand side of that thing. Okay, so we want to generate C in such a way that C's first row is B's first row plus B's second row. C's second row is exactly same as that of the second row of B, and C's third row is exactly same as that of the third row of B. Okay, so let's just try to rewrite it with everything. So we will not miss row 1, row 2, row 3 anywhere. So we'll write 1 times row 1 plus 1 times row 2 and 0 times row 3 for row 1 of the product matrix. Row 2 of the product matrix will be 0 times row 1 plus 1 times row 2 plus 0 times row 3, and C of row 3 of C product matrix is 0 times row 1 plus 0 times row 2 and 1 times row 3. So if I write this way, we get this one. So row 1 is equals to this particular matrix times this particular matrix times B, which is important, in the sense that all these values are coming directly from the above uh, picture. So you see, this one is coming from this, coming to this one is coming to this 0 is coming here. Similarly, this 0 is of the third row, so it is coming here, right? So you can generate this matrix and you can try out with your hand. If you take a B matrix with some rows, if you take C, or if you want to make C as linear combination of B's, then you can prepare a matrix, a multiplier matrix of B, which will be multiplied from the left hand side of B, so that C can be generated. So the job that you hold now is to know, or is to find out this particular matrix which can generate uh, certain thing, or certain linear combination of rows of B. Okay, now same thing that you can apply in the columns. So if you want to generate columns, you have to go through column matrices, and you have to put the multiplier on the right hand side. So multiplier has to be on the right hand side to make it fine. So you can see here you have another question where you need to generate only two columns from two columns of B. So you are generating two columns, so you are getting this example. Here we have multiple rows and we have two columns, and that's how we are able to generate again two columns, because the multipliers are supplied from two different columns. So the right linear combinations are provided by this one and this one, right? So these multipliers are actually helping us to generate these two columns. So these are the vectors that are supplied, and these are supplying the uh, scalar multipliers, and these are supplying, this particular matrix is supplying the column vectors for which the linear combination has to be taken. Okay. So there are a few more questions in this particular exercise which you can try, and we will utilize this idea in actually formalizing importantly, because what we were doing in the Gauss elimination process, we are trying to make a linear combination of the previous rows so that we can knock out some particular variables coefficient or make it zero in the equations coming later on. So we will try to do the same thing in the next video, which will help you in executing the Gauss elimination process with matrices, and that will be a great thing to understand. Okay, thank you.